Hello, everybody. Welcome back. We have a lot of content to complete. Let me go back to the Okay, let's start where we stopped. Just now we defined the different ways to quantify the concentration, right? We have mass concentration, we have the mass fraction, we can use mole concentration and mole fraction, right? We also see they are related to each other. Yeah. Now we see for air or for ideal gas mixture, right? Air can be treated as ideal gas. Ideal gas means the a gas that obeys perfect gas law, right? We have the perfect gas law, perfect gas, we say. Yeah? The pressure, volume, and temperature obey this perfect gas law. Okay. R is a gas constant for different gas, and what's the relationship between the? Basically, we see for a perfect gas, the mole fraction. The mole fraction is actually equal to because for perfect gas law, this will be equal to particular n, okay, times the universal gas constant. This is RU T, and this is a constant. Okay, you have, I think, if this is perfect gas, obey this law. Therefore, the partial pressure, which is what do we mean by partial pressure? Let's say you have a gas here, right? You have a mixture of two. Let's say you take away all the other gas, and you only have one gas left. In your room, let's say your room is full of oxygen and nitrogen, right? If you tell the air, all the oxygen leave this room, please. If all the oxygen leave your room, only nitrogen remains, right? Then the pressure in your room become much lower. Yeah. Now that pressure of only nitrogen is called the partial pressure of nitrogen. Yeah. Okay. And that is the definition. I think it's not that difficult to understand, right? Okay. Now here we say for a perfect gas law, the partial pressure ratio, the partial pressure over the total pressure is actually equal to the mass fraction. Yeah. So this is something This is something especially applied for perfect gas. Yeah. Okay. Well, this relationship will be useful later. Let's see. Yeah. Okay. Very simple. Let's first have a look at the so-called stationary medium consisting of two species, the fixed law of diffusion. Yeah. And I think here in this equation there is nothing unusual. The only thing you can see that we have two different equations. If we are talking about mass conservation, you see it's all the same. Okay. For if density is constant, you see if you are calculating, sorry, this is a typo here. This is not R. This should be a rho density. Okay. You may take a note. Yeah, this is the density. If you use mass concentration, still the equation the same. In other words, for this equation, if rho is constant, yeah, you can use either mass concentration or mole concentration. The only difference that you end up with different quantities, yeah, or on the mole basis or on the mass basis. Yeah, how many moles per second per square meter is passing through? Because here we are talking how many kilogram of per second per minute passing through. Yeah. So if you can use different units for the concentration, but you end with different units for the mass flow, and that's it. Okay. So remember, in other words, you always have the same diffusion coefficient, but you use different. You just use different. Either you either use mass fraction or mole fraction in calculation. You have a density here, but you don't have density here. What you get is different. Is that you have a different unit. Either it's a kilomole or kilogram. It okay. So this is different from the say conduction heat transfer, where you only have the temperature difference. You don't have so many let's say phases, right? Okay, it's a bit troublesome, yeah. Okay, but it's not that difficult to understand. Okay. So here is the analogy, yeah. And in heat conduction, in heat mass diffusion, the difference is here you have two different ways. Here you use the concentration gradient, but here you can also use you can either use mass concentration or the mole concentration. That's the difference. Yeah. And about this binary diffusion coefficient, binary means 2, right? Okay. That's because here we are talking about AB, yeah. Binary coefficient. Here you put it D A, okay, in air. This table just tells you the different gases of A. A could be oxygen, carbon dioxide, hydrogen, or nitrogen oxide. Nitrogen oxide is a pollutant. Pollutant means harmful species in the air, harmful to our health. Yeah, and also it depends. The D depends on the temperature. Okay. And here is the mathematical expression of how the diffusion coefficient varies with pressure, okay, and temperature. Now, here we are talking about at 1 atmospheric pressure how the diffusion coefficient varies with temperature, okay. And here is more, okay. Different how air diffuses, okay. DAB or DBA are the, one thing probably you should know is DAB or DAB is the same. Yeah. Okay. You have two different species. They're the same. Here we talk about different chemical species in air. Yeah, the diffusion coefficient. Okay. And here you have this. I mean, you have two columns here. Yeah. And here is a different species. Say carbon dioxide in benzene, yeah, and oxygen in benzene, yeah, or benzene in oxygen. Okay. Here you have some. Here has something more. Yeah. This is here is gas in liquid. Okay. Gas in liquid solutions. I mean, a very tiny word. Now, here is ammonium in water. Okay. For example, do we have methanol? Do we have ethanol? Let me see. We don't have ethanol. Okay. Ethanol is actually in water. Actually, it's alcohol. Okay. Alcohol in water. How it diffuses. Yeah. And okay, this is one. Second is a solid. Yeah. Oxygen can be, can diffuse into natural rubber. Yeah. Okay. And one solid into the other can diffuse into other. Yeah. But normally we say solid molecules fixed in one position, but actually they can migrate. But you look at the coefficient; they are very tiny, 10 to the minus 20 or minus 20. Yeah, very slow diffusion. Yeah. And here we are saying here we talk about particularly it's about water molecule in air in this case. Yeah. Again, these two are equal to 2 oxygen in air or air oxygen. Water in air or air in water is the same. Okay. That's in gas. In a gas. Yeah. Right. Okay, so this one is also talking about the diffusion water in vapor in air, water vapor in air. Yeah, it's diffusion coefficient. There is an equation. Okay. On this page is talk about the mechanisms of diffusion. Why? You may ask question, why molecules diffuse? Okay. In other words, why the molecules can move from one place to the other? Yeah, and well, the basic mechanism is a so-called Brownian motion. Yeah, molecules, they bump. Liquid and gases, they don't stay in one place. They bump onto each other very often. Yeah, so that is the basic mechanism. So I won't because of the time limit, I will skip this slides very quickly. You may read this afterwards. Okay. Now this is something that you have to pay attention. At the boundary between the two substances, say water surface and air. Let's talk. Let's say how the water evaporates into air. We know, right? Now there is something very different. What is the say mass fraction or the mole fraction of water in water? It's almost equal to 1, right? Because it's almost 100% water. Of course, you have some small amount of air mixed into water, but still the mass fraction of water is equal to 1. Yeah, or mass fraction or the let's say mole fraction almost equal to 1. But on the air side, immediately the mass fraction of air, of water in the air, or the mole fraction, drops. There's a step drop. Okay? We call it a jump in concentration. Yeah. So if you express this y, okay, as a function of x, here by y we mean the y of H2O, water. Okay, if I draw it, this is y. Yeah, this is different from our normal xy coordinates. Okay, this y is not really y, it's y water. Yeah. And so this is the function of y water along the x direction. Yeah. In mathematics, you know this is not a continuous function, is it? No, here is a sudden change. Yeah, this is not a continuous function. Okay. And this is something that you pay attention at the say surface. Unlike temperature, the temperature of a species on the two sides of liquid gas, or even liquid or solid gas, okay, the interface are not usually the same. When we talk about temperature, we would draw it this way. Yeah. It may not be it may not be smooth, but it is continuous. But in this case, it's not even continuous. You have two values at the same position, where air side, water side are different for the concentration. And this is very important. This is the fundamental difference between mass transfer and heat transfer. Yeah. Okay. So this concept. Second, we have this so-called solubility. Yeah. Okay. For gas, for liquid side, we define a Henry's constant, which relates the liquid side mole fraction with the gas side partial pressure of a species. Yeah. Earlier I mentioned about okay, select gases in water. Yeah. For example, we talk about oxygen diffusion into water, right? And then the water side oxygen partial concentration, let's say it's this one, Yi water side. Then on the air side, for example, it's pure nitrogen. If it's a pure oxygen, this will be 1 atmospheric pressure, right? And then we have this H, Henry's coefficient. Okay, that relates the two sides, the water side, okay, liquid side, water side, and the gas side. Yeah, this is a way to relate the non-continuous two quantities, air side, water side. There is a ratio. Yeah, and this is Henry's constant. Okay, this is very important. And this is the same table. Yeah. So you remember the concentration of a gas. Yeah, and so the partial pressure of the gas. Yeah. Therefore, there's three quantities. Concentration of gas is dissolved in a liquid. Okay, that is this one. Okay. PA gas side, that is the quantity we are talking about here. Yeah. This is the relationship between the two. And that H is the Henry's constant, which you find from this table. Okay. The next quantity is very important. Is this for solid? Yeah. And this is about the gas side concentration is related to the liquid side, okay? And this one is about how the gas side concentration related to the gas side times a pressure at saturation pressure, okay, of the gas side. Yeah, okay. so that's something about the gas side. Okay, this is about the boundary relationship. Is about the liquid surface between the liquid and gas. Now the next part here is about the gas concentration and the solid surface. Okay, solid. Somehow we don't use Henry's constant, and we define so-called solubility. Okay, solubility. Yeah, and here this S. Now this S is a Greek letter S. Okay, Greek letter they write it this way. They put S here. Yeah, that's how it looks like. Yeah. Okay. And this is the pressure on the gas side. Okay, so this is permeability. I'll put it this way. This again is a Greek way to write letter P. Yeah. Okay. This one. This is called permeability. Yeah. Now we first define a solubility, that's S. Yeah. And this slide is a bit confusing because this S is solubility of a gas in the fluid. Yeah. Again, because at the solid and gas surface there is a jump of concentration. Therefore, we define two terms. Yeah. Which relates the concentration of the species in the solid side and to the partial pressure on the gas side. Yeah, and by this coefficient, this is called solubility. Yeah, okay. Maybe solubility is here. This. Yeah. Then further, we define permeability, and that is time the solubility time the diffusion coefficient within a solid. Why? Because in this way, the calculation of the this is the solubility for different gases in different solids. Okay, this is the solubility here. What's the use? Again, we should understand because the jump at the surface, so we need this relationship. Okay, how the relationship is used? Let's look at this 1D diffusion problem. And this is very similar to the 1D conduction problem. In principle, this is what you can calculate. Okay, the concentration difference at two sides, yeah, and divided by the divided by the thickness of the wall. Time diffusion coefficient. Here you can use the this mass concentration here, right? Okay. This is very similar to the one-dimensional steady-state heat conduction. Okay, nothing different. Basically, this is diffusion coefficient resistance, right? And this is heat transfer. Remember, we use this analogy: heat transfer over heat transfer conductivity resistance, right? Okay. Now we have the mass transfer. Now we have the mass fraction, and then we have this mass fraction resistance, which is this one. Okay, you may say there's nothing different from, well, very similar to conduction. Yeah. And similarly for the cylindrical wall, I will skip this part. Again, it's very similar. You have this, you have this lock for the cylindrical wall, right? Otherwise, it's very similar. However, there is a difference. If you use the pressure of the air side, okay, remember within the solid wall, you use the solid side parameter, it will be the same as the conduction. You use the diffusivity, but if you use the gas side pressure, you would use, okay, you have to use this, you have to use the solubility or the permeability. Yeah. Okay. In addition to the diffusion coefficient, you have to take into account the surface jumping phenomenon, and this is the difference from the conduction heat transfer. You know, in the heat transfer, you only have one temperature applied both to the air side and to the solid side. But in the diffusion calculation, you have to distinguish between the air side concentration and the solid side concentration, which would be used taking a different value by taking into account solubility. Okay. Therefore, if you are familiar with the heat conduction, now we are familiar with the mass diffusion as well. So long we take into account the surface specialty, that is the solubility parameter or the Henry constant. Okay. So with that, I think we have a good understanding of mass diffusion transfer. Okay, in gases, now in liquids, now also through a solid wall. When the surface is involved, and the surface difference is involved, we can also calculate it. Okay. So those are the equations we have learned so far, and basically that is what we wish to I wish to communicate with you today about the diffusion, mass diffusion, and for our profession, the next thing is that water vapor migration to buildings, or migration. Yeah, and here basically through a wall there could be a moisture mass transfer, and which we should try to minimize it, especially for the building located especially for the basement. Okay, for the floor material, you know, in heavy rains, the ground is very wet, right? You don't want to have water migration into your building, and for that reason, okay, understanding the water migration is very important. Yeah, and in fact, there's nothing different from the equation we have used. Okay, first thing. Second, the practical relevance is that moisture or water is very damaging to the building structure, but also to the indoor air quality, because many microbials, that is molds, can grow within moist environment, which is bad for your health. Okay, molds generate a lot of toxic material for your health. If you have asthma, then you may experience health say breathing difficulties. Yeah. I'm pretty sure most of you have suffered asthma in your childhood. You have, if you ask your parents, I think 1/4 of a quarter of you would have experienced such a symptom. Okay, and we have this big data, and in fact, mold growth is a big problem. Okay. Second, in a very cold climate, the moisture in the structure can cause freezing. In other words, when moisture freezes, it expands, it damages the structure of the building. Okay, and in fact, that is one of the test problem one of the problem in test 1. Okay. So here we are in this lecture, because time, we're not going to talk about the calculations. You should have this common sense that for that reason we use vapor retarders. What is vapor retarder? Well, in isolating heat, we use thermal insulation materials, right? But then in retarding heat, retarding moisture, we use some special plastics or metal films that has a low permeability or low diffusion coefficient, okay, to increase the resistance. Yeah. In that sense, for example, this container, this wall will not, okay, it will be very difficult for moisture to permeate through. But if you use this film on your wall, it will help the moisture to go through. Yeah. See, this is where, for this film, we want moisture transfer to happen. For this container, we don't need it. Yeah. Okay. Therefore, for your building wall, we want material that does not allow moisture to transfer. But for this special application of say deodorizer, okay, or dehumidifier, you have the word, I don't know whether you can read, very small letter here, dehumidifier. Yeah. Okay, you want a material which has a higher diffusion coefficient. Okay, so with that, let's take another short break for 5 minutes. We start at let's say 40. Okay, 11:40. Now in 5 minutes, we start our tutorial sessions. Okay. Start recording. Okay, so then you calculate the mass fraction for the other two species, oxygen and carbon dioxide. Basically, if you know the total pressure, the total pressure of the mixture is known, right? The partial pressure is that, first of all, what is the partial pressure? Yeah. Like I said, really you have three species, okay? Oxygen, CO2, oh, I don't know why it's not, doesn't listen to me well. Okay, nitrogen. Well, if you say, well, this room is too crowded, then you have three rooms of the same size. And you separate the three, okay? Then each room each species occupy the same volume as they originally occupied, the same room. Yes. Then the pressure in each room will be different. Will be lower than the total pressure when they are together. When they are separate, okay. What's happened? Did somebody press the? I think somebody pressed my screen. I can't move. I cannot control my screen now. Who is pressing my screen? Wait for a second. I need to connect my power cable to my notebook. Okay. Okay, here back to this page. Yeah, and so this is the meaning of. I just now explained the meaning of the. Oops. Okay, the partial pressure, and so long you know the molar fraction, you can calculate the partial pressure from the total pressure. Okay, so that is Dalton's law. Okay. Determine the binary diffusion coefficient. This is another question of carbon dioxide in air. Carbon dioxide in air. Yeah. What is the binary diffusion? That's a D. Basically, we're talking about dCO2 in air. Or the air and CO2, they are equal to each other. In gases, these two are equal. Yeah. At 200 K, and this is very cold, right? This is basically minus 173 degree almost. Yeah. Earlier we said we talked about the dry ice, right? And I think CO2 can be frozen into ice at minus 170 degree. Talking about this low temperature, I don't know whether you have any of you having had a vaccination. If you've been vaccinated using any one of the vaccines developed recently, you know that one of the vaccines developed by Pfizer and BioNTech is a very cold temperature storage, right? Minus 70 degree, and okay, that is actually they use nitrogen to cool it, to store it. Yeah, anyway, 400 K and lower pressure and high. This is high temperature, high pressure. This is basically high temperature, low pressure, and this is low temperature and normal pressure, to see how the diffusion coefficient varies. Yeah. Well, this is basically you have to know the base first. Yeah. Basically, we know the CO2. We have to find a table at air at 1 atmospheric pressure. Yeah. And at table, you can find at 1 atmospheric at different temperature. Then we have the equation relates to the D at different pressures, okay? And from the 1 atmospheric pressure, you only need to modify it, but divided by the pressure. So basically, from this equation, of course, given in the handouts, right? In the higher the pressure, the basically lower the diffusion. Okay, you understand? Yeah. Also, from this original data, you see The lower the temperature, the lower the diffusion. Yeah. The higher the temperature, the higher the diffusion. You see. Okay. Yeah. This is give you idea about the diffusion coefficient. Yeah. It's not a. It's a very dependent on the pressure and temperature. Right. Okay. Therefore, this tutorial example is more about a concept. Yeah, a concept about the diffusion coefficient. Okay. I don't know. Here we're talking about a room about 25 degrees. And okay, here the vapor pressure, basically we're talking about the partial pressure of water vapor in the air. That is 3 kilopascal. Or 3,000 Pascal, right? Okay. Well, right now I'm going to do something. Okay, this is another a poll. Oh, your response very quick. Here we say the partial pressure water vapor in the room. Just now I draw the room, right? Say the partial pressure water vapor is only about 3,000 Pascal. Here I did a test. What's the total pressure of air in your room now? Let's say you are not living on the. I hope none of you is living on the high plateau. Okay, we are talking about the sea level pressure. How many pascals is it? I got the answers. I didn't give you. None is the figures given. None, I tell you, none is exactly the right figure. Which one is closer to the actual atmospheric pressure? One atom. How many pascals? And okay, I only got 3 responses. That means only three of you are listening to my lecture now, right? The others are not present. That's great. 11 have no responses. You are not here, are you? Okay, that's very disappointing. So. Okay, anyway, for those of you who are here, the number 5 is I think is closest, right? I think should be equal to yeah. So it's about 101 kilopascal. Yeah. And okay. So anyway, in terms of partial pressure, water vapor in the air actually is very tiny. Yeah? So it's only it's only this much, 3,000. So it's about it's about 3%. Okay. So that's the. But anyway, the question is ask you a different question. Yeah. 3 meter high, 10 meter wide dry wall. This about this wall. Yeah. I draw it. The solubility of water in the wall. This is the solubility. Remember the Greek letter. I show you how to write. Right. S. Yeah, solubility equal to this much. The diffusion coefficient in the wall also given. Determine the mass diffusion rate of water vapor through the wall. Yeah. The vapor pressure in the wall, in the insulation is negligible. That means on the other side of the wall, okay, let's say here is negligible is equal to the P, okay, P water is equal to 0. Yeah. Basically now the question tell you the water vapor pressure in the air on both sides. It asks you to calculate the diffusion, the moisture transfer through the wall. Yeah. You see now you need 2 parameters. Yeah. Okay. Now I clean this board a little bit. You need 2 parameters. The diffusion coefficient is D. Oops. This is D. Yeah. And this is the solubility defined by the Greek letter S. Yeah. And in addition to the thickness of the wall. Okay. So that is that's what the equation look like. This is the so-called dry wall, and this is outside is the insulation. Yeah. And and you calculate the diffusion of the water vapor through this wall. Okay. So you use the solubility. Okay. The water density of water in the dry wall. You first you consider within the wall what is the water vapor. Say the molecular, say the mole concentration within the wall. Okay, and you use the solubility here. This is the solubility. This one. Okay. On the other side, because it is 0, therefore the solubility you don't need to do calculation. It's also equal to 0. Yeah, because the pressure on the other side is equal to 0. Okay. In other words, by using the solubility, you first calculate the wall, the concentration within the wall, rather than directly using the concentration at the wall surface. Yeah. So this is different from the heat conduction transfer calculation. Okay. Then once you know the those values, then you can use the diffusion equation. Okay, you calculate the mole transmission. Then you can, if you want to calculate the mass concentration, you can times the molecular weight of water, basically water H2O, right? You can remember the atom is 16 and H2 is 18, so this is basically 18. Yeah, okay. That's it. Another concept which you probably, I don't know, for many of you, you will learn this in your year 3 subject, HVAC, air conditioning fundamentals. That is what we call relative humidity. You know, every day we listen to the weather forecast about the relative humidity, right? 94, 97%. What does it exactly mean? It actually means now in the air, let's say today, I think it's, let's say it's 80% relative humidity. And it actually means it's the actual partial pressure of water vapor over the so-called saturation pressure of water vapor is about 80%. What is the saturation pressure? Well, let me show you. Okay, let's say this is, you have liquid water here, right? You draw a vacuum here, vacuum the above space. What's happened? After you vacuum, the water still evaporate, right? So above you have the vapor, and below you have the liquid. Okay, therefore it will be balanced. So it's a vacuum space where you hold liquid water evaporates. So there's a vapor pressure here, and that vapor pressure equilibrium at corresponding to a temperature, depending on the temperature. Let's say temperature is today is 30 degrees. Yeah. Well, at different temperatures of the liquid water, you have a different saturation pressure here. Okay. If you have a rainy day, on a rainy day, the air will be saturated. The partial pressure in the air will be equal to the saturation pressure of water. Yeah. So we have 100% humidity. Okay. So that's what the relative humidity means. It is it means how high the pressure is in comparison with the maximum pressure possible in the air. Okay. There's something else. It's not part of the mass transfer, but it's a concept related to the partial pressure of water vapor in the air. So when the air, well, is saturated, it means if the partial pressure within the air reaches the saturation pressure, what's the implication? What does it mean? It means if you want to dry your clothes on that day, you hang your clothes in the air to dry it. But if the air is 100% saturated, your clothes will never become dry because the air does not absorb any moisture anymore. Okay, so that is the saturation means. Yeah, on a rainy day, if it's been raining for a whole week, and you hang your clothes outside in the air. I mean, not under the rain, even in the say on your balcony, your clothes will not be drying because there's no mass transfer between your clothes and the air in terms of moisture. Okay. Okay, so let's move on to another example here. Here is a thin plastic membrane separates hydrogen from air. Well, okay. Here a plastic membrane. Well, you may consider your balloon is not plastic. Balloon is rubber. Rubber membrane. Okay. Here we have the molar concentration. Okay. The binary diffusion coefficient hydrogen in plastic is this one. Yeah. So on the two sides, well, let's say. This is okay. Outside this is air. Let's see. Okay. Inside it's hydrogen. Let's imagine this is the balloon. And here the balloon, the diffusion coefficient already given. It's 2 millimeter, 0.1 millimeter. Okay. Now this question is funny. Funny in the sense, the molar concentration given here is in the membrane, at the inner and outer surfaces. Can you imagine that once, for example, you are given a balloon, you fill up your balloon with oxygen, you will only know the pressure of the part. If it's pure hydrogen, you know the pressure, and you can calculate the mole density. That's it that is in the balloon, not in the membrane. Yeah. For the air, we know probably the hydrogen in the air is 0. Yeah, that's what we know. I think in reality, that will be the quantity you are given to calculate the diffusion through. But this tutorial is tricky. That they already told you what's the mole fraction within the membrane. Well, in reality, you don't know. But in this question, it is given. And then the calculation becomes very easy. Okay, and well, it has a lot of discussions here. I think it's you can almost ignore them. The final calculation is just becomes such an easy calculation. Yeah. Here you don't involve the so-called solubility, okay? Because you only involve the parameter within the membrane. Yeah. So solubility is not involved, only the diffusivity. Yeah. But the point is, in this problem, there is something given is not realistic. In reality, you don't know. You don't know what's the fraction within the material. You only know the air side, the gas side information. So you would need to know the solubility of the material before you can do this calculation. Okay, so this is a very hypothetical problem. Yeah. Why? Because as I emphasized, at the surface there is a relationship between the air side, the gas side, and liquid side. Yeah. So typically, the property within the material, the concentration within the material is not known beforehand. Yeah. Okay. I think with that, we finish what we are supposed to learn today. In the next lecture, we are going to talk about the convection mass transfer, and especially the simultaneous convection, heat convection, and evaporation happening between the water surface and the air. Okay. On the global scale, the atmospheric environment or the climate is very much determined by this process, but the evaporation from the sea. We are talking about climate change. We are talking about ice melting. Okay, we are talking about rain and snow. That's because the convection from the sea. For our profession, we are air conditioning engineers, and primarily we know how to calculate the convection mass and convection heat transfer from the water surface. In our profession, we have cooling coil in air conditioning system. We have cooling tower to reject heat from the chiller, okay, water chiller to reject heat so that we can provide cold and dry air to indoor spaces. It's all because we know our profession knows how to calculate the convection mass and heat transfer. Okay, so the next lecture is very important. If you want to work in our profession with confidence, okay, with the sound fundamental knowledge, you should not miss my next lecture. Yeah, okay. So with that, I think I finished the lecture today, and the rest is for the next lecture. Yeah. With that, lecture is over, and see if